I watched you spin the globe, and when it stopped, you spun it once again, half as fast, in reverse. You said, let's go to where it lands. But Phoebe, you know how much you hate catching trains, and you never wanted to go back there again. Get homesick before you've even closed the door.
Looks like we're streaming. Well, hello.
Phoebe, I know.
Well, we're streaming. Looks like we're streaming. Okay, so we did a choice of 2 topics today. One was rays per second, speed, number of rays, etc., and memory access, and I had something to say about that. And one was spheres out of voxels, and spheres out of voxels was the one that the Twitter audience clamored for, so that's the one we'll look at today. And so I will quickly boot up the tracer and see what it looks like now, because I don't remember in what state I left it. In fact, okay, so why is this not working correctly? I'm yes, good. Let's try it again and see if I can do it without the trap. That's the red window that comes up. Yes, very nice. This is the active oberon system, or AOS, also called A2, also called blue bottle at various points in time. The ETHZ kept changing the name for some reason. This is a modern operating system based on oberon. I don't have time to explain it now, but it's probably responsible for my success in software development. In any case, we see here I'm starting up. Okay, so this is what we were left with yesterday. So here we have spheres, in fact made out of blocks, but they're not smooth shaded spheres. And I'm going to show you how I make smooth shaded spheres out of ordinary blocks. Yes, ordinary blocks. And how that's done. And I should have, in fact, not stopped that. Because actually I have a fragment of the sphere available already to show you. 5. Escape. Actually, I believe I do have something of a sore throat. Now that I'm talking, I can tell. I just sound sort of hoarse. Okay, so when I click the mouse button, there's a certain voxel that I draw. Space, a block, and it changes. There's a fractal cube. This one. There we go. That one there, which we can draw. Okay. Good. So now we're see those things that look like little eighths of a sphere? We did that. Turning off gravity now. Make the drawn voxel smaller. There we go. So I will dig a little tunnel out of these. Great. Trying to get an environment where we won't be disturbed by falling out. Okay, good. Okay, so these things here are, what is that? Quarter of a sphere, not an eighth. These are quarters of a sphere. Just as good as a sphere, really. It's the same principle. And they look smooth, as you notice. And the reason they look smooth, when you get up, when the camera gets close to them, they are obviously made out of cubes. So if we look at the limb, or the edge, it's jagged. It's made out of cubes. And if we get close enough, it's obvious it's made out of cubes. But we get far enough away, it looks like a smooth curve. And the reason is that when we're up close, it is shaded according to the surface normal of the cube, and when we're further away, when the ray hits it, it's shaded according to the surface normal of the sphere that the cube is part of. Got that? Okay. So when the ray hits a certain point on the surface of one of those cubes, there are two ways of calculating how bright it's going to be. I mean, it's got a color, but there's two ways of calculating the brightness. There's no lighting here, except that if you want, you can think of the light as being fixed on the camera. So there's a light on the camera. The camera is shining directly to surface, then the dot product of the ray and the surface normal. If the surface is pointing directly at the camera, then the dot product is going to be 1. And we multiply that by the color of the surface, and we get the maximum brightness. If the surface normal is pointed at 90 degrees away from the camera, we get a dot product with the ray vector of 0, and so on. So it's merely a question of which surface normal you use. Do you use the surface normal of the cube or the surface normal of the curve, the sphere? Well, we interpolate between them depending on how far away the camera is. So there's a smooth transition as we get closer. There's a certain point where the surface normals are all calculated according to the sphere normal, and there's a transition point where they are mixed, and then they're all cubes. Okay, so that's all well and good. I hope that wasn't too repetitive. If that's fixed in your mind, I'll show you the code for it. Okay. So I'll show you the code for the let's see. Okay, so the cube that's hit is going to be a textured voxel.
Left a mess.
Wait a sec.
What? Sorry.
Or is it? Alright. Just where is the code? I haven't looked at this code for years, so. Well.
Sorry.
Okay.
Sorry.
It's going to be in TextVox. That's not a textured voxel. You know, I don't really know where that code is anymore, because I would have to look for that code. I don't have it right to hand because I haven't been working on that code and I probably haven't looked at it for 5 years. So I don't know what file it's in. It might be one of my anonymous files, which are like, so it might not even be imported. Okay, so I don't have TextVox, voxel 4.
Like a mess.
Okay. So the easiest way to track this down is go to the marsh. The marsh is the sort of the garbage module where I instantiate everything we're looking at in that world. Okay, so we look for the sphere. Sphere. Mirrored sphere, no.
That's why. That's why. That's why.
I think Zot. That looks right. Okay, so let's look for this file. So I have this sort of like Baroque system of modules with these like hash type names. Let's see. Okay, no, that's not right. It's just a cube with a picture of Lord on it. It's not going to help us. Nothing against our Australian friend. Or, no, New Zealand. She's from New Zealand. Okay. Okay. Here we go. I don't know how long I can keep this up. My eyes are not. I'm having some like eye. But you can see the code. I'm having some like migraine type symptoms. Like It's kind of bothering me with my eyes. So okay, so okay. Well, let's try this.
Let's fly.
Oh. Okie doke. 5. So now we'll do that. I won't even attempt to explain what I'm doing here, except that this is not part of the code file. I'm actually executing a command in the operating system here. And what it should have done is put the object yeah, okay, nothing. Great. So why can't we... Okay, so no. Take that away. Good. That could have been the problem. Slot 2. Noise. Cross your fingers. Yeah. Okay. So here we're getting less than 10 frames a second, but there's lots. It's not the occlusion that slows us down. It's actually the fact that we have lots. We're looking past lots of occlusion. So there's lots of memory faulting. So this is like smooth, shaded. Oh man, this less than 10 frames a second is horrible. Okay, let me fix this. Okay, so I'm not going to change what's drawn in the world. I'm just going to like make it make the mist much, much darker. Anyway, I hope you accept the fact that these are like not spheres, but like quarter spheres. It's much easier to see what's going on with them actually, because you don't have to tunnel into them to see the structure. Not good enough. Let's see. Good, thank God that whatever that was, that wave was, it seems to have partially passed off. So I'm just setting numbers that are specifying the color of the mist with which I'm filling the world. At some point, the mist is really going to hit you. You'll see. And whereas with mirrors, a rasterizer can't do them at all. A rasterizer can sort of fake colored mist. I mean, OpenGL can do like mist. I mean, not really. Here, I've put in lots of mist. Ah. I see what's going on. Okay. Right. Okay. The red mist is applying, and in fact is too thick. We'll make it 20. 20. 20. But when we're in a massive area of those sphere sections, there's no mist at all, because there's no mist with the spheres, which we can change. But we'll make this the same color as the world. This will be amusing. I have two screens here, you see, and that window pops up. And the other one I have to drag it over. Yeah. These partial spheres are expensive to look through because of the way that space is subdivided in them. Anyway, I made them blocky. You see, they do kind of look blocky. That's because they're not made up of very many cubes. I have them on a... So if you think about the cube, it's basically a sphere hewn out of a... You can think about it. Think about a 16 by 16 by 16 block. That's so you can see it. But it'll of course look much smoother if we change it instead of being 16 to being, say, 64. And you'll also see that they're thinner now. That's because they... Well... And... Yes. So there you have it. Perfectly smooth appearing curved surfaces made up out of cubic blocks. Mist, mirrors possible, all at interactive speeds and full screen, soon to be in 60 frames a second full screen when we get a few more cores. But and because there are great advantages to doing real-time graphics this way out of voxels. I'm not possibly these are not all obvious at once, but okay. So it's not just that you can do things like, because everything is made up of blocks. You can make the world in such a way that you can destroy the blocks. You have geometry for the whole world. This is my point. Alright, so I can make holes. Now it so happens that because of the way I've written this, that when I change one of these objects, when I make holes in one of them, I make holes in all of them. That's because they're in fact all the same object. You can call it instancing if you want, although I don't. That's actually easy to change. In fact, it's easy to make a world of all shared objects like this, but merely make it so that when I start drawing in one, it replaces itself with a copy of itself. And so but a world structured this way is actually sort of interesting in that, oh, there's a mirror.
That's why.
There's a fractal. And I really want to thank the mysterious person on Twitter who voted in the poll, because this has turned out really well. I think this is really a fascinating world to float around in, and I never would have done it without your encouragement. This is just great. Oh, of course, I can have blocks of many different sizes in the world. Because, they're all just pointers to things, if you want to look at it that way, or objects is another way to look at it. Which means that, an object can contain a pointer to itself, and that, of course, is how to make a fractal. If you just take a 3 by 3 by 3 cube of objects, and make it so that some of them point to the whole thing, it's pretty easy to make a Sierpinski cube. And in fact, this is exactly what happens. Wow. So, back around 2005, 2006, I made my first movies of this render. I would have to fly around in a very small window with the mouse, with very poor resolution. And then I had a bigger window. I would capture the path that I flew on, and then I would replay that path, and I would have a bigger window, and I would capture each frame of the output, which would take like 3 seconds. Snap as a BMP image. I would go to sleep sometime with my computer chugging away. It would save thousands of these BMP images. Then I would have to FTP them from my Oberon machine over to Linux, and then mass convert them to PNG format, and then bind them into an MPEG movie. That's the way I would have to see what it would look like if my render was in a little better resolution. I'm sure that was before YouTube existed. So you can hear the parrot now, I assume. It's flapping its wings in chortling. Okay, we're not really getting anything out of this. Alright, thank you for being with me.